Yes, it is
Okay, I
started
think
already.
it's not a recording. Yeah.
Perfect.
I welcome everyone again back to the third day of this meeting, the quantum computing workshop, and um, Sugam, you can start.
Yes,
Start.
okay. Yeah, okay, thank you. Okay, so in the last class, we discussed about the stone Gerlach experiment. And based upon that, we also discuss about the spin. So I will start here from spin. So the expression of a spin operator is the idea taken from the angular momentum, because you can see that for the orbital angular momentum, if this L operator is operating on the its eigenstate, then the output will be a L plus 1 h cut square and ml. Similarly, if Lz operate on the ml, so it gives us a ml h cut ml. So this analogy is taken for the spin also. So in the spin also, we have a operator like S square, and the corresponding eigenstate I can just represent like S and ms. So accordingly, this S is going to be SS plus 1 h cut square. And same way, I can define the Z component of the spin. That is going to be a MSH cross. And then define the other two components. So for example, SX and SY. In general, we take help of the ladder operators. So ladder operators like, you know that when S plus operate on this, then I mean, this kind of mathematics algebra, you can go and just look back to the now your textbooks, and there it will available easily, and I hope is not a problem. And here it will be a ms plus 1. And similarly, S negative we can define. Everything is same, but here the sign will change. I'm doing this writing this equation just to make sure that there's a flow, and this SS and this X component of the spin is defined as the S plus and S negative. And similarly, the Y component by 2 iota. And you can see this Sx, then now you can calculate. No? So this is going to be simply 1 by 2 and S plus ms and S negative. And same way, you can do for the other part as well. 2 iota and minus m. So you have all these components, and these actually everything written in analogy. from the orbital angular momentum. And still we don't know exactly what is the values of this spin, but spin of course can take half integer values, can be 1/2, 3/2, and so on. So from there, one can calculate the matrix form of these operators. Maybe this you can take as a task. You can try just graduate or master level problem. So if you want to write down the matrix of this S square, so what you can do that? You can just try to calculate this matrix element, and this is nothing but a delta function. And if you look at, I mean, so you can calculate this quantity delta function for different spin components. So maybe you can try to do this for, let us say, spin for spin half particle. So for spin half particle, if you calculate, then this is going to be this delta function you can calculate. This is going to be a 1, 0, 0, 1. And accordingly, you can see that this matrix element, okay, or the matrix representation of this S square is going to be a 3/2, 3/4 actually, H cut square, and 1, 0, 0, 1. And the same logic you can apply, and you can calculate the matrix element for the SZ. That is going to be H cut by 2 and 1, 0, 0, minus 1. And similarly for the S plus, similarly for the S negative, and similarly from there you can find out the Sx also. So Sx will be going to be a H cut by 2, 0, 1, 1, 0, and Sy will be a H cut by 2, 0, minus iota, iota 0. So I just try to now show these all uh, uh, equations just to let you understand that how these operators can be represented in the matrix form. And once you know this operator matrix forms, you can calculate the eigenvalue and the eigenfunctions. So you can apply this on the state, maybe on the psi, and let us say whatever eigenvalues you have, you can calculate. So this is the equation to calculate the eigenstate and also the eigenvalue. So these are the some basics, okay? And you know that when you talk about what we need is the Sx. So for Sx, the eigenvalues are 2 plus minus h cut by 2. And the eigenvalue I can call, let us say, s plus 1. So one eigenvalue going to be a eigenfunction going to be h cut by 2, and 1, 1. Oh, sorry, that is going to be 1 by root 2, 1, 1. And other will be s negative, 1 by root 2, and 1 minus 1. Similarly, when you look for the sy, again the eigenvalues are plus minus h cut by 2. And I think I'm using like this, Sx plus and Sx negative. Similarly, Sy plus is 1 by root 2, I'm writing because we need to, we're going to use these now equations 1 by iota, and sy negative will be 1 by root iota. And similarly, the last one is the sz. So for sz, again, lambda will be cut by 2. And in this case, sz plus will be 1, 0, and sz negative will be 0, 1. In general, generally, this one is what we call as the 0 represent, and this is we're going to call as the 1. So this is how generally we represent our spin operators, and then spin eigenfunctions and corresponding eigenvalues. Similarly, we can try to look at, let's go back to our SG experiment. So in this experiment, I told you that if the magnetic field is aligned along the z direction, and a beam is coming from the, let us say, some oven, and there is a, let us silver atoms. So unpolarized beam is going to come out. And so here, actually, you are measuring the z component of the spin, means you are applying the sz operator. And whenever you're going to apply the sz operator, so this sz operator is going to apply on the unpolarized beam. And when this is going to act on this, then you're going to get two beams out of this. So one is going to be a sz plus and sz negative with eigenvalue h cut by 2 and with eigenvalue minus h cut by 2. So this is what we did in the last class. Now, let's do one more little bit extension. What if I pass this to another Stone Gala experiment, which is aligned along the z direction? I mean, again, I'm going to measure the sz. So what you're going to see here, that you're going to get only one component, that is the sz plus. Second component will not be present here. And further, when you're going to pass it to another SG experiment, which is aligned along the x direction, means I'm going to measure Sx, then you're going to get further two beams. So one is the Sx plus and Sx negative. And then, I mean, majority of the quantum mechanics books, you will see that the interesting parts arise when you're going to block this part. And again, you pass this one through the z component. I mean, again, you're going to measure the sz component. Again, you're going to get the two beams, sz and sz negative. And this is happening because, so I can show you mathematically that how it happens. Why? I mean, initially in the stage 1, you already blocked the beam sz negative, but now this beam is again reappearing. So this we can explain very simple, no? Because when, for example, look at the first step. In the first step, when you're going to do the sz measurement, here, whatever beam you have, okay, that the state is, let us say, defined as psi, then this wave function you're going to write, okay, I mean this psi, you must write in if you want to operate Sz, then you have to write this wave function as a linear combination of the eigenstate of Sz. So it will be a C1 and Sz plus and plus C2 Sz negative. And now when you're going to operate this Sz in the first step on this psi, what will happen? Can somebody will tell what will happen when you're going to apply Sz on the psi? Anybody will like to?
Hello, sir.
Yes,
If you,
yes or
if
no?
you, yes, if you operate SZ, then it will pick up and down both component from that SZ.
Ah, okay.
Oh.
No, it's not like that. Anybody else? So see, we did in the last class about the measurement problem in the quantum mechanics. So whenever you're going to do a measurement, then what happened to wave function? The wave function going to collapse, correct? So this wave function psi is going to collapse. It will collapse either in Sz or either in Sz negative. There are only two now eigenstates. So it will collapse either to Sz plus or it can collapse to Sz negative. Is this clear to everybody? The wave
Yes, sir.
function going to collapse. It means that if it collapses to, let us say, Sz plus, then this Sz is going to operate only on the Sz plus. And in that case, it is going to give value what? H cut by 2 eigenvalue, and Sz plus will be there. And if it collapses to the Sz negative, then it means ki Sz is going to operate on the Sz negative, and then you're going to get a minus H cut by 2 and Sz negative. So this is the reason that why you are getting these two values. You can see here. So when this Sz operator operate on this wave function psi, this state or eigenstate, this arbitrary ket is going to collapse either to this state or either to this state. If you do only one measurement, so it will collapse to either this state or to this state. So either you will get this one or you will get this one. But since a large number of particles are coming, okay, and if you do large number of measurements, then because this is a measurement is going all the time continuously, so you will get half of the particle in this state, the other particles will go in the this state. So this is how you get these two beams. And now look at in the second stage. This is second step. In the second stage, what happened that this,
Hello.
yes.
So in mathematically in the equation one, when you have operated
Mhm.
as z on psi, so in
Yes.
principle you should get like h cross by 2 into sz plus some h cross by 2 into sz minus, and
No, this is
then
not this is not a mathematics, right?
no, but it's still, I mean, when you are saying something like that, this or this, so it would be better to consider like, I mean, I'm not able to get a, I mean, you are saying that the wave function is polar, but SZ operating SZ psi is not something like that you have measured something. So when you are probably looking at
You
like,
have measured something, yes. When you operate
uh,
SZ on the side, you have measured something. This is what I'm trying to say. This is a
but then the
measurement.
measurement is something like you take expectation value of SZ. So it
Exactly. So
rather than
you have to measure many number of times, correct?
so then you have to take psi sz psi, then only one can say that something with the 50% probability of getting sz or 50% probability of getting something like this. But I mean, just operating
See,
sz
you
psi.
are trying to say this is not true. I mean, this is not true to say that the SZ is going to operate on the SZ plus. and SZ going to operate on the SZ negative. No, this is not correct. Okay, because
Mhm.
once you this is a measurement now. When you going to even a single measurement, this is a measurement, correct?
Hmm.
So once you do the measurement, this wave function no longer remain the psi. Once this psi is going to operate here, I means once you pass this magnet through the magnetic field, it means you are doing a measurement. It is a single measurement, and
Mhm.
even a single measurement is going to cause the collapse of the wave function. Okay, so the psi will no longer remain the psi. It will going to either become this one or this one. The probability of getting collapsing in this will be C1 square, and the probability that it will go into SZ negative will be C2 square. But this is single measurement. I agree. When you are asking for the expectation value, then you have to do a large number of measurements. Okay, but even a single measurement is also a measurement, no?
Mhm.
Okay. So when this SZ is going to operate on the psi, then psi no longer remain the psi. This is what I discussed in the last class also. Okay, there is a particle and its wave function is like this way, and nothing but it is superposition of these many monochromatic waves, which is called phi 1 and phi 2 and phi 3, and this is the psi. And when you want to measure the momentum, okay, of this wave function, okay, what will happen? Momentum, let us say here is P1, P2, and P3. So definitely in a single measurement, you will get some value. And if you're getting the momentum value P2, then all these states will going to collapse. Although this is going to be a summation of Ci and pi I, but after the collapse, after the measurement, once you're going to do the measurement of P on the side, it will collapse either to phi 1 or phi 2. But let us say I'm saying it is collapsing to P2, then it is simply going to be a phi 2 will survive. So the P operate on this one, and this is what you get the output. So even a single, when you operate as operator on the side, it is a measurement. It is a single measurement.
Hmm. Okay, fine. I'm
Okay.
actually thinking in terms of some mathematics. Like for example,
No,
let's say
it is not a
SZ.
mathematics. This is what I'm telling. This is not a simple multiplication. Okay.
SZ has the mathematical notation 1 0, and then SZ minus is 0 1 in the matrix notation, and then SZ, which is on 1 0 0 1 a 2 by 2 matrix, and then operate on this. Then fine. So I will just think about it,
Okay.
and
Okay.
yeah,
Good.
later.
And in the second stage, what is happening? You're going to operate SZ on the SZ plus. And now you see this SZ plus is already a eigenstate of SZ. And I told you that then the wave function will not collapse because it's already eigenstate. It means this is going to be simply going to give a h cut by 2 into SZ plus. So this is the reason that you're getting only one value here, one component, SZ plus. Now look at in the third stage, you're going to operate Sx. On which state? You're going to operate Sx.
Sir, what will be the form of psi after step one, stage one and stage two?
No, for spin, there's no functional form available. Okay.
Psi will be this psi wave function at the beginning, which you take it, right?
Aha, okay. It will be
What will be its
just
form?
it will be like this way, correct? It is a monochromatic.
You know, in terms of mathematics, at the first stage, you consider phi as C1 SZ plus C2 SZ
You
minus on that form.
So
the
I
early
think
the
yeah.
earlier one you said this one, correct? I mean in this case, in this example.
Yeah, it's fine in this way, monochromatic, group velocity, other things. But in the form of mathematics, at the beginning, you choose psi as a C1
Yes,
SZ
phi
plus
1
C2.
equal to is something like iota, let us say P1 x upon h cut. This is how the functional form is going to look like. And similarly, the phi 2 will be e power iota P2 x upon h cut. So this is the mathematical form of the eigenstates. Okay.
Okay, sir.
Okay, good. So now you see, I'm at the third stage. So let's look at why you are getting again Sx plus and Sx negative. So here this Sx operating on the Sz. Now since this Sz is not eigenstate of Sx, so what we do? We must express Sz as a linear combination of eigenstate of Sx. Okay, so eigenstate of Sx are Ss plus, Ss negative. So what we do first of all, you're going to write down Sz as a, let us say, a C1 and Sx plus and C2 Sx negative. This is the first step. You must express the ket Sz in the linear combination of the eigenstate of Sx. Remember, in the last class I told you, if you know the eigenstates of any operator, then any arbitrary wave function psi can be written as a linear combination of phi I. And if you have another operator B, and you also know the complete eigenstates of these operator, then the same wave function can be written as a linear combination of eigenstates of the chi I. So you can see that this state, which you can call as the wave function also, so this can be written as the eigenstates of the operator Sx. And now
Shouldn't
you can,
C1 and C2 be different?
yes, I mean, you can call D1, D2 maybe here. And then you can apply the Sx on this Sz plus. And what will happen? This state is going to collapse either in this state or in this state. So once you go into the measurement, the wave function going to collapse. So you will get either a Sx plus or you will get a Sx negative. And it means now this Sx going to operate on this, then you will get a plus h cut by 2 and Sx plus. And when here it is operating, that is going to get a minus h cut by 2 and Sx negative. So you can see you're going to get this Sx plus, Ss negative. So two beams are again going to appear at the output. And now it become very simple to prove that why you going to get the Sz negative. Because when you're going to operate this Sz again, look at in the fourth step, operate on the Sx plus. So to do this one, I have to write down this Sx plus as a linear combination. Let us say E1 of Sz plus and plus E2 and Sz negative. And now you can see when you're going to operate Sz, so it is again going to collapse in this state or in this state, or you will get either Sz plus or you will get Sz negative. So it means you are operating Sz plus here, so you will get h cut by 2 and Sz plus, and you operating Sz negative here, so you will minus h cut by 2 and Sz negative. So you can see that why this Sz negative again reappear. Okay. So this is how in the quantum mechanics you can understand the operation in steps. And why I'm telling, because this is something, I take a very simple example. I will go into a little bit difficult now. I will take a arbitrary direction of the spin, and then we will do the same thing there also. But please let me know if anybody have any doubt up till now. I hope this sequential Stern-Gerlach experiment is clear to everybody. So shall we go ahead?
Yes, sir.
Good. Now, here we said very confidently that our magnetic field is along the z direction. Now imagine what if the beam from the oven is coming, and you pass it through a SG experiment, but that is along some direction, n dash or n cap, and corresponding operator I can call Sn cap. What will happen? Geometrically, it is something like this way. So imagine that this is the X direction, Y direction, and Z direction. So in the initial examples, we took the magnetic field along Z direction. Okay. So, but now what I'm trying to say here, the magnetic field is along this direction. So let us say this is the n cap. That is the making angle at a theta along that direction. So what will be the situation then if you going to have this condition? Are you following what I'm trying to show here? The meaning of this direction?
Yes, sir. Now
Good.
we are just
Yeah.
taking the arbitrary direction.
Yes, we are taking some arbitrary direction. Okay, then how you going to do this whole mathematics? Okay, so today you will get assignment, and in the assignment I have given this as a question to solve you. Okay, so question is that you will see that so question that you have to construct Sn operator and also find its eigenvalues and eigenstates. So this is the one assignment question I have given to you. So you see here that it's very simple to now construct this one. What I can do, I can just take the projection along the XY plane here, and I can define one angle phi also. So I'm saying that the spin, that operator, no, this Sn operator is actually equal to S dot n, where this S nothing but xi cap, xyj cap, and szk cap, n dot. Now you can see here, this is going to be a nxi, nyj, and nzk, and where this nx, ny are the unit vectors. So you can see that this is going to be then sx, nx plus sy, ny, and sz, nz. And you can see that the x component will be what? This is going to be a sine theta and cos phi, correct? Similarly, ny component will be sine theta and sine phi, and nz will be equal to simply a cos theta. And this sx already you know is actually equal to h cut by 2, 0, 1, 1, 0. And here you have a sine theta and cos phi. Plus, similarly, you can expand this one. You can do this exercise yourself. And at the end, you will see this Sn operator in the n direction. It comes out to be a h cut by 2 into cos theta and e power minus iota phi into sine theta, and similarly e power iota phi into sine theta into minus cos theta. So this is the operator. So when the spin, when you try to apply the magnetic field along the z direction, along the any n direction, so in that situation, the operator now of the spin, okay. So if you look at along the z direction, then the operator form is h cut by 2 and 1, 0, 0, minus 1. But when this is along n direction, then this is the how this is going to written like. And you can see that you can reconstruct the matrix. No? So when you SZ, when you talk about SZ, SZ means theta must be 0 and phi must be also 0. And you can see that you will going to get the same value. And when you talk about, let us say Sx, so Sx means theta must be pi by 2 and phi will be 0. And you will see that you're going to end up with this matrix that is called 0, 1, 1, 0. The same matrix is going to give this value, the same matrix is going to give this value. And similarly, you can see when theta equal to pi by 2 and phi also pi by 2, then that is going to give a Sy, and that is h cut by 2 and 0 minus iota, iota 0. So you will get all the spin components, operator forms from this general. So this is general equation, general form of spin operator. So I have written the this operator form, and I want you to proceed this to find eigenvalue, which of course going to be a plus minus h cut by 2, and then also find eigenstates. So this is a task you have to do, okay? And I hope this is not going to be too difficult for you. So you can see that when the eigenvalue is plus h cut by 2, then corresponding eigenstate that I can call Sn plus is going to be a cos theta by 2 and e power iota phi and sine theta by 2. And when the eigenvalue is minus h cut by 2 and the corresponding eigenstate is actually equal to sine theta by 2 and minus e power minus iota phi into cos theta by 2. This is like, this is such that given this Sn operator operate on the Sn plus, you're going to get a plus h cut by 2 and Sn plus. And when this is going to operate on the second eigenstate, then you will get eigenvalue minus h cut by 2 and this is negative. So this is something you have to prove. This equation or all this equation and this equation. This is part of your assignment. You have to do it, and I will use it directly here for our purpose. Anything you want to ask up till here before I move to the Bloch function or Bloch sphere? Fine, shall we go ahead? So now coming back to the SG experiment, and this is our tasks today. No, this is where we're going to spend our time, because from here then our quantum computing things will become much easier. So you see that we have a beam from the oven. It is going to incident or pass through one SG experiment in which the magnetic field is oriented along the n direction. Okay, and that n direction already I given to you. It means you going to do measurement of the spin operator in this direction. Now, I already shown you above that this will split in two parts further. So one is going to be give a Sn plus and other will be Sn negative with the eigenvalue plus h cut by 2 with the eigenvalue minus h cut by 2. All right. And this operator, this vector Sn plus, and just a minute. So these are the two beams you're going to get. And again here, if I block one beam and let other beam to pass through, another SG experiment in which the magnetic field is along the z direction, then what you going to get? That is our task here. So what I'm doing here, I'm going to measure the SZ plus. It means I'm going to operate SZ plus on which state? Sn plus. So can someone tell me what I need to do if I want to operate this SZ on the Sn plus?
Yeah, we will express in terms of eigenstate of SZ, no?
Exactly. It means you have to express this one as a linear combination of eigenstate of, so here what I can say, so I have to operate C1 into SZ plus and C2 and SZ negative. And if you want to calculate the C1, how you can do it? I can have this inner product. I'm right. And when you do this part of your assignment, you can see that this Sn plus, then I can express in this form. Already it's given, no, not difficult because I already written the Sn plus, Sn negative. It means I know the vector, so I have to express this one as like this, cos theta by 2 into Sz plus n plus e power iota phi into sine theta by 2 into Sz negative. So this is how I can express the Sn plus in terms of the eigenstates of the Hz operator. And now you can do the measurement on this Sn plus. What will happen that this wave function is going to collapse either in this state or either in this state. And accordingly, you will get either a Sz plus, and in that situation, Sz will operate and you will get a plus h cut by 2 and Sz positive, or it will collapse to Sz negative, and that is becomes then minus h cut by 2 and Sz negative. So you can see you're going to get again two beam here. And here I can just write down, maybe now it will be very useful for you. This Sn plus is actually equal to cos theta by 2. Maybe I can just represent by 0, because this state Sz plus is sometimes also called 0, and it is also called 1. And plus e power iota phi and sine theta by 2 and 1. Whereas the second part, look at the matrix above, I already written, it is going to be a sine theta by 2 and 0 and minus e power iota phi into cos theta by 2 into 1. So you can see that key how we can express these two eigenstate as a linear combination of the eigenstate of Sz operator. So I have already given one more question in your assignment. Okay, if this is the situation, okay, then what is the probability? So look at here, this gives the eigenvalue h cut by 2 and minus h cut by 2. So question that what is the probability of getting plus h cut by 2, and what is the probability of getting minus h cut by 2? Anyone will like to tell me how to do this? How you can find the probability?
Well, you have already written Sn plus in terms of Sz plus and Sz minus. So the probability is mod psi square. So Sz plus operating on Sn plus, and then they take mod square.
Exactly.
So
Exactly.
then
This is
cos square theta by 2 and sin square theta by 2 is your.
bilkul. So this is going to be a Ci. This is a formula to calculate, and this is going to
Yes.
be simply a cos square theta by 2, and getting this will be simply a C2 square and the same, and this is going to be a sine square theta by 2.
Shouldn't S negative have e to the minus I phi?
No. Which one?
S negative.
You mean Sn minus, right?
No.
Yeah.
Why? It should be same, no?
Minus e to the minus I phi cos theta by 2 times.
It seems like e to the power minus I phi.
No. When you take the complex conjugate, that will cancel out.
It will be plus.
Okay, thank you.
So these are the values. So our objective here. So these are the questions now I just framing so that you can find little bit easy when you look at the assignment today. So you can try to look at the assignments, and we will just for practice something. But this state, no, which I am calling as a S n plus, and now onward maybe I can call as the n plus also. So this is equal to cos theta by 2 and 0 and plus e power iota phi and sine theta by 2 and 1. So I will use this one. So this is a spin vector, okay? And where you can see that now what I can do now, I can draw a sphere. So let's think about this x-axis and y-axis, and this is the z-axis, and maybe I can just to show that this looks like a sphere, not a circle. So you see that in this 3-dimension, as I mentioned that this spin I can represent as a vector, maybe this dot. So this is my vector that is called n plus. And here is the angle we define, theta. And if I look at the projection, so it will go somewhere here. And this is the angle along with x-axis, that is I can call as the phi. So any spin vector I can represent with this vector n plus. And this blosphere, this is what is called the blosphere. This is the, I can say, a way, okay, way of representing. Representing spin state in spherical coordinates. So we can represent the states on this blosphere, and look at this vector which I'm representing. This vector, the tip always going to lie on the surface of the sphere, and this can rotate. Now, for example, look at if theta equal to 0, and in that situation phi doesn't matter, so I can take phi 0 also. So this n plus, you can see that it is simply going to become 0, nothing but a sz plus. You can see that, so this is the one state. So here, maybe I can just show by a red dot, okay? So this is the state I am representing as a 0. Now look at when theta is going to become pi and phi is again 0, then this n plus is going to become what? Look at the equation. This is become 0, that is going to be simply 1. Nothing but a sz negative. So you can see that on this blosphere, this is the point representing the state 1. So this is the upspin, and this is the downspin. So on the blosphere, the North Pole, generally we call top as the North Pole and the bottom as the South Pole. So North Pole representing the spin up state along that direction, and the spin down state is shown on the South block. And further, you can see in the same equation that if we can represent so let's see theta equal to pi by 2. So you are in the xy plane, and then phi is 0. Then you can see that this n plus become what? This is going to become cos 4 cos pi by 2 means pi by 4 and 0, and plus e power again 0 and sine pi by 4 and 1, and this is nothing but a 1 by root 2 and nothing but a 0 and plus 1. In the matrix form, this is nothing but a 1 by root 2 and 1 1, okay, because 0 is nothing but a 1 0 and 0 1 nothing but a 0 1. In the matrix form देखोगे तो क्या बन जाएगा 1 1. This is nothing but a sx plus. So you can see that here at this position, I'm just trying to spend some time on the blosphere because once you are comfortable all the positions, okay, then it becomes much easier for us to deal, okay. When I will discuss the qubits and gates operation, because when I talk about a gate in quantum computing system, so gate are nothing but they are a operator which are rotating this vector. Which vector? This Sn plus vector. So some operator, for example, think about the situation of, we'll talk about uh, poly X gate. So poly X gate is nothing but when you operate poly X gate on the 0, it's going to make it 1. Or when the poly X gate operate on the 1, it's going to make it 0. So technically, what is the poly X gate is doing? It is rotating this spin vector, okay? I mean, in this case, it is going to rotate from the north to south pole. So that is the north pole, and this is the south pole in this situation. So this is how the poly X gate going to do. So all the operators, they're doing nothing, but they are just going to rotate this vector on this sphere. So this is a reason that we need to little bit now focus and try to remember or get familiarity all the locations of the blosphere. So for example, here, when you talk about this location, so this is the position theta pi by 2 and phi 0. So here, this is nothing but a theta equal to pi by 2 and phi 0. And this is nothing but a x plus, or maybe I can call as the sx plus, and this is nothing but a 1 by root 2 and 0 and 1. So you can see that. Similarly, you can further calculate for other values. For example, if we talk about theta equal to pi by 2 and phi equal to, let us say, pi, okay, then what you will get? Anyone?
Sy.
This is give sy, and you will calculate, then you will see that this is going to be 1 by 2 and 0 and 1. In the matrix form, this is going to become 1 by root 2 and 1 minus 1. This is nothing but a sy negative. Sorry, sx negative, correct? You will go back side now. So you will go here somewhere. I mean, this is the back direction. So you will be here at this point. So that is the location where the theta is pi by 2, but phi is pi. So this is the position where I will mention that this is the location where I can say theta equal to pi by 2 and phi equal to pi.
Minus.
Exactly. So this is the sx minus. There is nothing but a 1 by root 2. Let me drag this side, and this is going to be a 0 and minus 1. Similarly, you can see when you are working at theta equal to pi by 2, but let us say phi is pi by 2. Then you are at this location, correct? Here. And I will just write down directly now. So this is the position. So this is the position where theta is pi by 2.
And phi is equal to pi by 2. That will gives sy.
Exactly. So this is going to give a sy plus, okay? And when you
Yes.
solve this part, this is going to be a 1 by root 2 and 1 by root 2 0 and plus iota 1. And you can see the last part when theta, I mean, you want to go to this location. So this is the location where the theta is pi by 2. And what is the phi value? 3 pi by 2, correct? Sorry, a angle जो है, that angle will be like this way. Okay. I mean, you're measuring from the x-axis, so you can just move and come here. 3 pi by 2, and you can see here, this is going to become then
SY
sx
minus.
sy minus,
Yes.
and this is a 1 by root 2 and
0
0
minus iota 1.
iota 1. Very good. So this is how you can locate, okay, now the spin states on the blosphere, on a different blosphere, oh, sorry, on the bloss surface. So take a minute, okay, and just try to absorb it, and also let me know if we have any further question.
Yeah, hello, Sugam.
Yes.
No confusion regarding the mathematics, but one clarification. So we are now doing it explicitly for spin qubit, right?
This we are doing for the spin qubit, yes.
Yeah. So now let's say we take a different qubit, let's say photon qubit or any other qubit. So mathematics as well as the
same thing remain the same, because for example, in the case of photons, you can represent with the polarization vector, correct?
Correct.
So all mathematics remain the same.
No, but then the operator like SXX, these are explicitly for spin, no?
Yes.
So the Bloch sphere concept will be the same, that I realize, but the mathematics will be different, no?
Mathematics will be different, yes.
Okay.
Yeah, 100% true.
Okay, yeah.
Sir.
Anybody else? Yes, please.
Sir, we have talked about the X gate, I mean poly X gates. And it seems to be, is it a unitary matrix?
This is all gates are unitary matrices. Okay, I will talk in detail about unitary matrices, definitely. I just give the example just to make sure that you understand the logic behind discussing this Bloch sphere. So because all these gates are going to rotate these vectors. Fine, so shall we move ahead? So I mean that question he asked is very valid. I mean this Bloch sphere must keep that here we are using the spin half particle. So there is a spin operators. So the mathematics will be completely different for the when you're going to use for the photons. In principle, Bloch sphere can be used for the photons, but the mathematics will be completely different. Okay, so if no further question, then I can share something with you. So this was the basics of our quantum mechanics, and this is the part we done very well. And from now we are going to move into the quantum computing part. Okay, so before just a minute. So can you see my screen? I'm showing some slides.
Yes, sir. We can.
Okay, good. So you see that now formally we are going to discuss the quantum computing. So these are the some slides I mean already talked about these first computer, and then how these after this first computer, which was made of the vacuum tubes in 1947, just 1 year later, then Bardeen developed this uh, contact not transistor, and after that system has never looked back in principle. So, and I told you that the size of the transistors are reducing very fast, and we are already in the regime where the this length L is shrinks to around 2 nanometer, and if it goes to, let us say, 1 nanometer, then electrons from this source, they will tunnel directly into the drain, and there will no role of the gate will be here in this situation. So you can see that uh, this technology is going to fail completely, okay, in this regime. And I discuss about the issues mostly people are now facing are two. One is the heat dissipation, or there is a quantum tunneling. Okay, so heat dissipation, because you are packing a huge number of transistor in a small space, and these transistors are not nothing but conducting electricity, and because of that heat is going to produce. So heat dissipation is the one issue, but the biggest issue is the, of course, the quantum tunneling. And to manage the heat dissipation, uh, one can go with the different types of transistors. Maybe one can go for the graphene or carbon nanotubes, and which offers better connectivity. And as a result, you can see that the heat connectivity will be much better. The heat dissipation will be much better in that case, because they are much better heat conductor. But to look at the solution of the quantum tunneling, okay, in principle, there's no solution I can say in the classical transistors. So in the classical transistors, you can't see any solution for this problem, okay, because this is a fundamental issue. When you talk about tunneling, so tunneling is a fundamental issue. But people are trying to now little bit push it further now for certain more years. I mean, the problem is they are trying to delay the problem by introducing some high dielectric materials. Just a minute. Yeah. So when you introduce dielectric materials, then what you can do that you can actually increase this. For example, here you can increase this thickness. So even electrons can tunnel from this region also. So this tunneling you can avoid, okay, or you can delay if you increase the dielectric material thickness. So this is what now one can do when you are using the high dielectric materials. But ultimate problems will still remain there. And this is what we're talking about, that the quantum computing is the only solution in this case. And now we will talk about how these quantum bits, superposition and entanglement, these three phenomena, how they're going to use full for the quantum computing. And this is what picture, just to show that the Murray laws, that it is already, the graph is getting the plateau, and there is no further now increment of number of transistors on a single chip. And so we will talk about the superposition. Already we have talked more about this. Entanglement, I will take a separate lecture for the entanglement, because that is something we need to discuss in detail. And quantum measurement, already we discussed how this wave function going to collapse. And everything is governed by the Schrodinger equations. Now, when you talk about a classical bits now, when you talk about a quantum computing, then the first thing we need to understand is the difference between the classical bit and the quantum bit. So for example, when you talk about a transistor or MOSFET, okay, so when it is a on or off state, corresponding we call as the 0 and the 1 state. Okay, so that is the uh, high and low state in the transistor, and they are called the bit. And using these bits, we can make different types of gates, OR gate, XOR gate. For example, here I have given the circuit diagram how to make a NOT gate using this MOSFET. So similarly, using this transistor MOSFET, you can make other gates also, which I mentioned here. And another diagram I have mentioned here is about the NAND gate. In our classical computer, NAND gate is also a universal gate. So using the NOR gate, you can construct almost everything. And using these gates, then we can do some arithmetic operation. So for example, using this XOR gate, so we can make this full adder. Full adder means how these numbers are going to be added. For example, if you want to add 0 and 1, then how it will add. I hope this is something already you are aware. If not, then you can just, I will share this slide to you, and you can just think about how these numbers are adding up. We can save some time. Now, coming to the quantum computing part. So we will talk about in detail, but I'm giving some overview so that your interest in the quantum gates and quantum circuits will develop after looking through these slides. So when you talk about a quantum system, so in the quantum system, we can use the quantum states to create a bit. For example, in the case of a spin, so I can use the spin up and spin down. Okay, so these two act as a bit, but they are quantum bits. Okay, so we call them as a qubit.
Yeah, so
Yes,
if I
yes.
want to understand, so let's say forget about some spin state.
Yes.
For example, if we have some other particles, let's say
Exactly.
if I have some, for example, let's say, I mean, I'm not sure if you are familiar. So if I have a neutrino, let's say neutrino particle, and it has 3 intrinsic state, so let's say alpha, beta, and gamma. So then, so for each state, we can define a bit. So you are calling it as a qubit, probably because you have a 2 state. So if we have a more than 2 states, then we call it as a, I mean, we can call some different. So for the quantum system, for each state, we can define a bit. So is this statement is correct?
Yes, in principle, yes, it is correct.
And if we have more than more than 2 states, then so we will be in a problematic situation, or I mean, it will be good for if we have a more states.
I think you discussed this earlier also, right? This question. See, problem is that in principle, you can work. Okay, no issue with that. Okay, so you can use one state, let us say 0, one state 1, and one state 2. So I think there is some word the people use D bit. Okay,
Okay.
dimension bits, higher dimension bits. Okay, so D bit is also a emerging concept. People are trying to utilize or create a quantum computing with more than 2 states. But only issue people are facing is creating gates. Okay, so creating gates are not going to be so easy, no, or it's going to be too complicated for them. Okay, if you go beyond
2 states.
2 states, so it is
Okay.
only the complexity is adding. But in principle, yes, you can use D states also. I mean, it's not only 3, but 4, 5, 6 also. But the complexity will going to increase. The complexity, for example, think about if you want to, let us say your state or your system is in this state, okay, and you're going to shine some photons or whatever you're going to do, and you want to make this transition downward and upward, correct?
Yeah.
So that is a problem. So I mean, if you have multiple states, okay, then in the multiple state, if they are equally spaced, okay, so if they are equally spaced and you are shining a photon, then I want to make this one to go to 0, okay, but this one can go to 2 also, correct?
Yeah.
So these kind of complexities are problematic, okay? And if you make, let us say, non-linear, okay? So if you make a non-linear, then for each transition, okay, then you need a different laser. Okay, so let us say the system is here, you want to make this transition and you want to make this transition, or you want to make this transition. So for each, because each energy is different, correct? Each catch H cross omega 2, H cross omega 2. So the problem will be solved. For example, if you shine photon here or H cross omega, then the particle is here, it will come down only, it will not go up, correct? Because the energy is, the gap is different. So that problem is solved, that one will go to 0 only. But then you will not be able to now make utilize the 3 states. So for that one, then you need another laser or another microwave of energy H cos omega by 2. So in that situation, to access each state, then you need a different frequency microwave or pumping source. So this is the complexity people are facing.
So that is why most of the example and people are talking about the 2 states of
2
qubits,
states,
because
exactly. It's a much simpler system to work, but
practicality, yeah.
practicality problem, exactly.
Okay, thank you. Yeah.
Okay, so well, coming back, so in principle, not only spin, any 2 levels, okay, can be used. And slowly, I will go further a step ahead, and I will show not only states, but even phase also. 2 phase can also be used, okay. For example, in superconducting, I will tell you that the phase is going to be used as the 2 states. Even in the photonics, a 2 path, let us say photon is going through this tube or this tube. So this also can be used as the 2 levels, to define the qubits. Phase can be used. Current is moving clockwise or moving anti-clockwise. This direction can be used as the qubit. And of course, in the quantum atomic levels definitely can be used to denote these states, okay, to define the qubits. But in topology, topological structures can be used for the qubits. But let's now little bit hold it. Let us try to first get familiar with the energy level system. It's much simpler to understand the qubit in the energy level, and then slowly you will understand how these different propositions, for example, current moving clockwise or anti-clockwise, can also be used as the qubit, okay. Phase can be used as the qubit. Topology can be used as the qubits, okay. So in principle, classically, if I say a coin, let us say with a head or tail, so there are 2 states, okay. So in principle, I can say there are 2 states can be used as a qubit, but practically you cannot use. I mean, because coin is a not a quantum particles. Okay, so you cannot use the head and tail as a to form a qubit. But in principle, if you look on the basic levels, so technically, if the coin is behaving like a quantum particle, then its head or tail, it can be used as the qubit. I hope you are getting what I'm trying to convey this message.
Yeah, fine. Yeah.
So here we are going with a very simple example, a spin up and spin down. And in the quantum mechanics, we can represent this as the 0 and 1, as I mentioned already. And but See, if I'm going to use only these two states, 0 and 1, okay? So there is no, mark this point, there is no difference between the classical computer and the quantum computer. So in the classical computer also, you have this 0 and 1. This is going to be off state, and this is going to act like on state. So if you want to use only spin up and spin down state and form a qubit, then there is no difference between the quantum computer and the classical computer. Okay. So if you operate, I'm again repeating, if you operate or if you limit the quantum computer only to these two states, the state 0 and 1, then there is no advantage of using quantum computer over the classical computer. So here, the third state, which we call as the superposition state. So we can create this state. So this superposition state, the superposition of 0 and 1. So this state, for example, when I was writing this, let us say Sx plus as a C1 Sz plus and C2 Sz negative, or maybe a C1 0 plus C2 1. This is a superposition state. So this state is also a possible state in the quantum mechanics. So in this superposition state, and this state is going to give you advantage, because look at very carefully. So what I'm let me conclude further. So we said there are two states, spin up and spin down, and these two states can be act as a qubit. So we have a qubit 0 and qubit 1. But I mentioned that this when you're going to use the quantum computer only in this state, then there's no advantage of a quantum computer. But there is a special stage that is called superposition state. So beside these two basis states, and remember, they also call the basis states or eigenstates. So beside these two basis states, we have this linear combination. And what is so special in this linear combination state or superposition state? The specialty is that to describe this state psi, I need two complex number A and B. So to define this psi or superposition state, I need to define two complex number A and B. It means this state is carrying two pieces of information. I will not call bit information, okay? There's no logic of bit calling here, because this A and B, they can take infinite values, okay? This A can take any values, no? B can take any values, okay? So there's no meaning of calling bit, but I can certainly say the psi contains information, because you are storing information in form of A and B. So there are two pieces of information is there. Is this clear? So the number of I can say complex A and B which are required, okay, to define this psi are 2. Similarly, the interesting part. So this is what I have written in this diagram. I will share this slide to you. And this is the difference now when you look at in the classical and the quantum. Okay, so if you restrict yourself only to this basis state, there's no difference. Okay, but this is the third state is going to give an advantage. Okay, because see, if you have one classical bit, then you can have only 1 bit of information. But when you have 1 qubit, then you have 2 pieces of information. Okay, so that wave function is going to have 2 pieces of information stored there. So I'm writing here the 2 pieces of information can be stored in a single qubit. Whereas in a single bit, you can only 1 bit of information. 1 bit of information. Now the situation you can see is becoming more interesting. Okay, and we will talk about this tensor product when I will come to. So when you have 2 qubits, so for 2 qubits, then I can define these 4 states. So there are 4 basis states. Remember, these are the basis states. So there are 4 basis states: 0, 0, 0, 1, 1, 0, and 1, 1. So they are the 4 basis states. And using these 4 basis states, I can make a superposition state. And now you can see, to define this wave function psi, I have to supply 4. I have to determine, or I have to uh, uh, give the value to this A, B, C, D. So I need 4 complex number. I need 4 complex number to define the wave function psi. Whereas when you look at the 2-bit of classical computer, so in 2-bit of classical computer, you can store only 2-bit of information. At one time, it will be only a 0, 0. Although next time it can become 0, 1, but still it is storing a 2-bit of information. Maybe in the next state, it can be a 1, 0, but still storing 2-bit of information, and same in 1, 1. So technically, only 2-bit of information is stored in the, if you have a 2-bit of, or 2 transistor, let us say you have a 2 transistor, 2 MOSFET, then you can store only 2-bit of information. But if you have a 2 electrons, then these 2 electrons, of course, going to have a 4 basis states, but along beside these 4 basis states, there is a superposition state. And to define the superposition state, I have to define these 4 complex numbers. So technically, there is a 4 piece of information is available with this wave function. Whereas in the classical system, you have only 2 bit of information. So I can say in the classical computer, if you have 2-bit, so 2-bit means only 2-bit of information only. But in the classic quantum computer, you have a 2 power 2 piece of information. Or I can say 2 power 2 number of complex quantities are required to define the psi wave function. And similarly, you have a 3, let us say qubit, means you have a 3 electrons, electron number 1, electron number 2, electron number 3. And you are using a spin of this electron as a qubit. So for 3 qubits, I need 8 complex number to define the superposition state of 3 qubits. I'm again repeating, I need 8 complex numbers, A1, A2 to A8, to describe the superposition state of 3 qubits. Whereas in the classical computer, if you have 3 transistors, you can store only 3 bit of information. Whereas here, you are having 8 piece of information. Similarly, if you have, let us say, n number of qubits, so you will have n number of basis states. N number of basis states. And there will be a one superposition state, which is the superposition of all these n number of basis states. And to describe, I can just go ahead here and I can say n number of such complex numbers. So I need n number of, sorry, 2 power n number of complex numbers to define the wave function. Here it will be a 2 power n, like this way. So I need 2 power n number of complex number to define the superposition wave function.
But again, all these statements.
Yes, you can complete your statement.
Yeah. So all these statements that you are saying about the qubits is a two-level system, right?
Yes, exactly. I'm talking only about the two-level system.
Two-level systems. So n is equals to 3 qubits means you have 3 electrons.
Yes, and 2 levels. Okay.
2 levels. Thanks.
Yes.
Yeah. Now, that makes sense. Okay.
So for n qubits or n electrons, then I need to define 2 power n number of complex numbers, okay, to describe the wave function of superposition of n qubits. So you can see that lots of information is there in this wave function psi. I hope it's clear. This point is very important, that for n qubits, you have a 2 power n basis states. And to describe the superposition state psi, I need 2 power n complex number. Lots of math required to do this one. But what I'm trying to point out here is that lot of information is there in this superposition state. So there's a huge information is there in the superposition state. And similarly, you can see that if you have n only 300, then for 300 qubits, there will be a 300 basis states. And then I need 2 power 300, mean 10 to the power 19 number of complex, 10 to the power 19 complex number to describe the superposition wave function psi, which is superposition of a 300 qubits. And the amount of information is how much? 10 to the power 19. So 10 to the power 19 complex numbers are required. And if you look at in the universe, you have number of atoms. Agar dekho, so it is only a 10 to the power 82, less than 82. So this amount of information available in the wave function psi is much more than the number of particles in the universe. I hope it's clear to everybody. So for example, if you have just a 300 electron, and let us say hypothetical case that key I want to encode, I have this number of atom in universe. So I want to encode, let us say one complex number, let us say A1 to this atom, and A2 to this number, this atom, A3 to this atom. So let us say I have a 300 electrons or qubits, okay, no, and I have a this size state of the 300 qubits, and I want to encode this A1 to each atom in the universe. Then I can tell you, I mean, you can see easily that you will have a scarcity of the atoms in the universe to store the information regarding this A1, A2, and AN. Okay. And just think about our classical computer, okay? It's a thought-provoking, means the total storage now, what we have now, maximum can be 2 10 to the power 21, I think, yes, 21 bytes. This is the total storage in the world. It's not enough, 10 to the power 21. And what are you talking here? 10 to the power 19. So, I mean, I'm just giving this example just to let you feel, okay, that quantum mechanics is very enormous. And just a superposition state contains huge information, lots of information. And that is the power in the superposition. And this is the reason that in the quantum computing, we talk about superposition, because superposition is the giving you the supremacy in the quantum system. That is what is called quantum parallelism. So when I say quantum parallelism means nothing but a quantum superposition. So for example, now you can think about, I told you earlier also, let's say you want to add two numbers, let's say 2 plus 3, okay? Now, if you try to take 2 electrons as a qubit, so I can represent now, maybe I can put one electron, let us say one electron in the state 0 and other in the state 1, correct? And these two numbers I can represent like a 1, 0, correct? And then another one as a 1 and another also as a 1 state, then I can represent this is 1, 1. Now, when you pass it through a quantum computer, okay, so in the quantum computer, what they will do, okay, so in the quantum computer, it is going to take all the possibilities of 2 bits, okay, so it will take possibility 0, 0, okay, it will take 0, 1, 0, 1, 1, 0, and 1, 1. And another possibility for the second also 0, 0, and 1, 0, 1, 1, 0, and 1, 1. Okay, so you can see that this number is 0, this number is 1, this number is 2, this number is 3, correct? This number is 0, this number is 1, 2, and 3. So what will do? The system, in the quantum system, what it will do? When you're going to put this one in the quantum computing system, so it will going to put this this into superposition. It means it is going to create a psi A1 0, 0 plus A2 0, 1 plus A3 1, 0 and A4 1, 1. So you are not only giving 2. In the quantum system, it will take all possible combinations corresponding to this state or this number. And then you have another psi 2 like this. Now you add this number. So 0 plus 0 is 0, 0 plus 1. So this will take all 0 plus 1. It will take 0, 1, 2, 3, 4, 5, 6, up till now. So when you're going to add these two numbers, okay, so it will going to, in the superposition state, it going to take all the poly values 0, 1, 2, 3, 4, 5, and 6. It means when you're going to add 2 and 3, so it will create a superposition state. And when you further add and still in the superposition, so it is going to create these numbers, but they will remain in superposition. So this is going to be in superposition, all possible results are there. So the quantum computer will going to calculate everything. So in the calculation, it will have an answer 0 also, answer 1 also, answer 2 also, 3 to 6 also. So it will have all possible answers, but it will be in the superposition. So I can say here the net result psi will be a, let us say a D1 0 and D2 1 and so on. Say later D3 6 up till here. And now when you're going to do the measurement on this state, it will collapse, correct? Collapse to 0, then you will get a 0 answer. It can collapse to 1, then you will get a 1 answer. And if the probability is same, then you will get all possible answers. But the answer should be 5. Then I will let you know in the quantum computing system, then there is a very important concept that is called the entanglement and interference. This interference we will do. I will tell you how to do this now quantum mathematically. Okay, this interference and how this interference will help to increase the result of 5 or probability of 5. It means you have a chi and the probability D1, D2, D3. So the probability of D5 will be higher. So when you going to do interference, then the probability of the 5 will be highest. And then when you do the measurement, the wave function will collapse. It will collapse in 0 also, in 1 also, in 2 also, in 5 also. But if the probability of 5, let us say 99%, then the chances that of getting answer 5 will be much higher. And this is how the quantum computer works. So before measurement, it will compute everything, but it will remain in superposition. And only after the measurement, you will get one answer. But if you are doing measurement without interference, you will getting all possible answers, no use. So before doing the measurement, you have to do interference, okay? So that the probability of the right result becomes higher. And then you do the measurement and that will give you the highest probability of the right result. I hope this message is clear to everybody.
Yeah, hello, Sugam.
Yes.
Maybe very naive question. Just if I'm going by this analogy, we need to know the answer.
Yes, no. I would not need not to know the answer. Just
Okay.
wait for only one day. Okay, I will tell you how this quantum computer is so nice way to. It's algorithm completely. Okay.
I see. Okay.
So we will prove it. I will take the Deutsch algorithm. Okay, and we will go step by step, and we will see. There's no need to know the answer beforehand.
Okay.
Okay.
So another thing again, I was going by this analogy. So if we have this one operation to do, we have 2 qubits, right? We are using 2 qubits. So likewise, for a complex operation, does it mean that we need to have more and more number of
yes,
qubits?
Exactly. And more number of qubits if you're using, then you can see that the answer will become much complex. For example, let us say you are using 3 qubits, correct? And you want to add 2 plus 3.
Right.
Then this is going to be a 0, 1, 0, correct? And other will be a and your quantum computer, then it will take all possible combinations. It will
Mhm.
be 0, 0, 0, 0, 0, 1, and so on, correct?
Mhm, mhm.
And when you're going to add it, so you will get answer from 0 to 17.
Right.
So 5 also will be there, okay?
Mm.
But if you use 3 qubits to start the calculations, then the number of possible answers will be much higher, okay? And in that situation, then you will be more in trouble. So
No,
it is
the third qubit we can reserve for the another operation, no?
yes, exactly. Then in that condition, then you can use this third qubit for another operation. Exactly.
Okay.
Yes.
So I mean, so for example, let's say I need to use it for an n-electron wave function calculation. It's a self-consistent calculation. So let's say for helium atom, does it mean I need only 2 qubits to calculate the wave function?
No. In the helium atom, then you're going to have plenty of the quantum states, correct?
Yeah. Let's say I want to get the ground state wave function for that case. So as usual, I mean, when we are solving the Hartree-Fock or the self-consistent equations, so here, I mean, self-consistent operations are many, many more in number, but we are using, we are doing it for only 2 electrons.
Yes,
So
only for 2 electrons you are doing, but this 2 electrons going to give plenty of quantum states, correct?
yes, right, right.
You want to actually simulate and go to you want to get those quantum states, no? You want to get the information of those quantum states. So don't only think about the 2 electrons, okay?
Okay,
You
okay.
have to think about here how many possible states are formed because of these 2 electrons.
Okay, okay.
Sir, regarding the storage you mentioned previously,
Mhm.
so I understand that you want to emphasize that we need a very huge amount of storage space to store that in an atom. But instead of using atom, what happens if we store them in a web?
A story now?
Web.
In
a radio wave, let's say.
No, I'm still not getting the correct
Uh,
meaning of the question you're.
no, you want to store the information, right, in an atom. So you need around 10 to the power 90 number of atoms, which is not present in the universe.
Oh, that
right?
was just no. That was not. I was not giving the okay. That was just an analogy to show that how much information is already there in the wave function psi. It doesn't mean that I really want to store that even in the atom. Okay.
Okay,
This
okay.
was just to analogy to show that the amount of complex numbers which are there in the wave function are much more than the number of atoms in the universe. That was the only meaning of that one. Okay. No
Okay,
other meaning.
okay.
There's no meaning to say that I want to store those complex number in the atoms.
Okay, okay, fine.
So are you already using some software to do this simulation for the helium atom?
No. I mean, I'm using the original Hartree-Fock codes.
Okay.
Yeah, those are the old conventional type calculations, self-consistent calculations that I'm doing. Yeah, not for helium, but for multi-electron systems and some of the engineered atoms and molecules. But those are either Dirac-Fock type or Hartree-Fock type calculations. Yeah, but not quantum computing level, the classical computing type.
Okay.
So in last example, how 17 is arrived, here I can understand probably. So
It will be, I
this
think, 16, correct? 15 hoga, right? This will be 8 and 16 hoga. This will be 16, no? Because this will become 8, last one. 2 power, this will be a 2 power 0, 2 power 1, 2 power 2. So this is going to be a 4 plus 6 plus 1. Sorry, 4 plus 2 plus 1, so 6, 6, 7. It will be 15, sorry. it will go from 0 to 14, correct?
So
0 to
you
15, sir.
Total will be 15.
2 to the power 0 to 2 to the power n. 2 to the power n is the total number of terms should be.
That's correct. Total 16 will be the total number of the combination will be 16. Actually, I would not keep thinking about this problem of the helium atom. That how many number of qubits actually. Okay, maybe I will try to now give some practical answer by tomorrow. Okay, I think still I'm not convinced with my answer actually. Because if you want to just try to simulate only a ground state or maybe one state, then you don't need to know about, you don't require too many qubits. But if you try to simulate, let us say, n number of states, then definitely you need that many number of at least qubits are required. But just give me a time, okay? Maybe tomorrow, no, I will think more upon it, that how many qubits actually you should be, at least minimum qubits, maximum whatever you can have. Okay, so coming back to what I was trying to just here. So this is the one now video I just want to show that how this quantum parallelism, okay, or quantum superposition, you can visualize now. So for example, you see in the classical system, if you want to go from here to here, then you have to try each and every path one by one, one by one, one by one, one by one, okay? And after many trials, then you can reach there, okay? But see, if it's in the quantum system, then the quantum system, it will going to explore all the path at the same time. And the one path will be correct path also. So for example, this 5, so it will try all paths 0, 1, 2, 3, 4, 5, 6. And one answer will be a correct also. Okay. But when you do the measurement, then you have to make sure that you get the right answer. And I will tell you how to do the interference to get the right answer. You don't require prior knowledge of the result to do the or to amplify the probability of the right result. So I think that's fine. This is what I wanted to convey this message for today. And tomorrow then I will be start discussing the gates, quantum gates and the quantum circuit.
Hello, sir.
Yes.
Sir, can I ask some questions?
Please.
Sir, my question is regarding some device-based parts. Suppose what component differ to make a classical computer to quantum computer?
See, 90% of the items in the classic quantum computers are classical parts only.
Okay.
So only one part. Okay. I think I have one lecture also where I will discuss the physical computers. So there I will discuss, for example, whether you talk about superconducting qubits. In a
Yes, sir.
superconducting system, then you need a dilution refrigerator. Okay. These
Yes,
are going
sir.
to have many stages. Okay.
Yes,
There will be a here is a 10 millikelvin stage, and there you're going to put a very small resonator.
yes, sir.
That is the quantum bits, correct?
Yes, sir.
And all the parts here, all the parts what are doing here, you can going to have a measurement system, supply system. So you can see 90% of the items in the quantum computers are classical. Okay, it's
Okay.
only that qubits, okay, are quantum.
Okay.
We
So
have a special lecture on this part. Okay, so we'll describe completely that. I mean, I will try to take at least 2 lecture on the physical system, because
Okay.
this see, I mean, these mathematics and algorithms, things you can study yourself also in the
Yes, sir.
notebooks.
Yes, sir.
Okay,
So tough to
the
visualize, sir. Only the.
so major thing is that how dealing the physical system,
Yes, sir. Yes, sir.
exactly how the quantum computer work physically. Okay, so
Yes,
there
sir.
I will take 2 lectures minimum where I will discuss thoroughly from A to Z. that how a conducting computer works, starting
Yes, sir.
from the supplying power pulse and measuring.
Yes.
Okay. Similarly, in the I will take one as a thorough example, and then other as only a basics. For example, ion qubits. Okay, and photonics. I don't know whether I will be able to discuss photonic or not. If time permit, we will go. But at least one system I will discuss fully.
Okay, sir. So up to now, sir, what I got is simply we have a two states and qubit in the sense a electron for which we are going to do the analysis or apply the algorithm, and superposition based study simply. So
Yes.
so
Yes, that's correct.
yes, sir. So I am curious about the how we can physically visualize the things. That's my
This is
question.
that was the basic objective of my these whole slides, and digging a little bit on the basics so that
Mhm.
you create your curiosity. Then only you will
Mhm.
be able to stick to the course till last day.
Mhm. Yes, sir. Yes.
Good.
Because these things we are familiar, sir, going
Yeah.
through the theoretical concepts.
Exactly. Exactly.
Yes,
Yes.
sir. Thank you, sir. Thank you so much.
So quickly, I will tell you tomorrow. I will tomorrow also. I will take some time because tomorrow. I will tell you not only mathematically how to represent the gates, but
Yes, sir.
physically how to make them, how to
Okay.
realize them in the laboratory. For example,
Yes.
whether you are working with the photonic systems or superconducting qubits, how to make the gates.
Yes, sir.
Hello, sir. This is
Yes.
Neha.
Mhm.
Sir, I need to ask about assignment. Where will we submit our assignment? And
I will give you on the WhatsApp group, and I will provide you the platform to submit the assignments.
thank you, sir.
Okay.
Sir, I have a doubt regarding that quantum and qubit and classical bit. Is it
Uh-huh.
shall I proceed with that?
Yes, yes.
Yeah. So what I get to know is that if you have a 2-bit like say classical, so we can
Mhm.
store at the time basically it can store 0 or 1. Fine. And what
Yes.
I get about quantum bit like qubit is like we can store 0 and 1, and apart
And
from
then
that
one
we can store superposition also.
we can have a superposition state also. Yes.
So is that the difference basically? Like
This is exactly this is the difference. I mean, so uh,
0, 1
we-
can be stored, but
uh,
superposition can also be stored in that also.
yes. So there is extra state exists in the quantum system, and this is where the quantum supremacy comes. You're right.
Okay, sir. Thank
Anybody else?
So thank you very much for this informative lecture.
Thank you very much to you also for attending these classes. So, Sunil,
Okay. Are we concluding now?
yeah, I think we can conclude
Okay.
now.
Yeah. Okay. Then I think the next class we will meet tomorrow.
Yep.
So I'll stop recording right now.